Okay, welcome to the module 1 of Sustainable Systems Design, Life Cycle Analysis and Industrial Ecology. In this module, we'll first learn about the field of sustainability science, a brief introduction. Then we will look at the three pillars of sustainability, the economic, ecological and social. And then we will talk about the first attempts to combine the pillars of sustainability, which is the IPAT equation and then the limitations of IPAT. So, what is sustainability science? It is a new field that has been emerging that seeks to understand the fundamental character of interactions between nature and society to encourage those interactions along more sustainable trajectories. This is the definition given by Cates et al. And if you notice, the emphasis is on the interactions between nature and society. So, your society involves both the economy and the technological developments, while nature is mostly the environmental systems. And we are not only concerned about the growth in the economic or the technical systems, but also how the natural systems are evolving. And in the field of sustainability science, our focus is on looking at the interactions and ensuring that both systems are growing and thriving well together. The current state of field, so what are we doing in the field? We are kind of focusing on developing a stronger analytic and scientific underpinning by bringing together knowledge from several fields together, which involves natural systems, engineering, social science, medicine, economy and politics. Since sustainability science is an emerging field, it has been around for 20 years, but relative to other scientific fields, it is considered relatively new. Hence, we are still focusing on developing stronger analytical methods and scientific tools. In this course, we will learn about few of those methods such as life cycle analysis and industrial ecology and some of the footprint methods. However, as the field is emerging, we look at those analytical techniques and we learn to adapt to the current knowledge and also apply to the current systems for the systems design. So, definitions. What does sustainability mean? By Brundtland Commission, this definition in 1987 was put forth, which was about development that meets the needs of the present without compromising the ability of future generations to meet their own needs. What that means is that it is not about only what we need to do today to meet the demands and the growth of the society, but also what we need in the future, or how does the future generations will respond. Hence, we say that we owe a lot to the future generation because we are using limited resources that are available on the earth. The pollution we create, the damages we cause to our ecological systems are really affecting the ability of the future generations to meet their needs. Hence, in sustainability, we take into account what could be the demands of the future, and hence we are talking about the trajectory or the sustainable trajectory of the interactions of nature and society. There are three pillars of sustainability: economy, ecology and society. So, let us look at what is the economic paradigm of the sustainability. In 1798, Thomas Robert Malthus wrote an essay on the finite principle of population, and that was led by the fear that growth in population could not be supported indefinitely without leading to poverty. This clearly mentions, or this clearly indicates, that how the growth of population is affecting the ability of people to get resources that are available, or through get the limited resources that are available, and hence this focus on the economic sustainability mentioned that as we are growing, we might not be able to meet the demands of all the growing population without some population living in poverty, which definitely relates to the quality of life. Then in 1865, Jevons talked about the finite supplies of coal could not support increasing Britain's energy consumption in his book, which was the Coal Question, an inquiry concerning the progress of the nation and probable exhaustion of the coal mines. After industrial revolution, of course, there was a lot of coal combustion, but Jevons found out that for the rapid economic growth, there was not enough resources, and hence it was not a sustainable exponential growth that they were going on at that time. Then in 1952, US President's Material Policy Commission, they also raised concerns about post-war economic sustainability due to the growth in the consumption of non-renewable minerals. Since the non-renewable resources are really finite, if you are consuming them at a rapid pace, there may be the rate of consumption will not be sustainable. And the President's Material Policy Commission found that for different non-renewable minerals that were available at that time and were important for the growth of the economy. Then finally, in 1972, Meadows et al. Published a very important essay which was The Limits to Growth, which clearly mentioned that the exponential economic growth that several societies or several regions of the world were going through was not really sustainable, and they really need to think about what is the sustainable growth. And that is where the term sustainable development focuses, right? When we talk about sustainable development, is that really the thing that is going to grow? Then there is sustainability, which is the ecological paradigm. So, in the sense of the ecological paradigm, when we talk about ecology, we think about how do biological systems remain diverse and productive. We know that the earth system has been existing for millions of years, and the ecological systems have an innate ability to maintain the diversity and productivity over several years. However, we have been thinking about some of the issues that the ecological systems are facing, such as the biodiversity loss. The UN Convention of Biological Diversity did estimate about 13 million species, out of which only 1.75 million species have been identified, and they have about 1,000 species have gone extinct, and there are about 10,000 that are on the IUCN Red List. So the question comes, are all species sustainable, and why are these species being extinct? Some of the scientists believe that, of course, climate change, the land expansion by human population, which is definitely the interaction of the humans with the nature, and the pollution is a key cause of these extinction that has been happening. So, from the ecological systems perspective, we are really thinking about the balance of what exists in the ecological systems and how sustainable it is with the growth that we are continuing to make on this earth. There are also geographical changes that we have seen, such as issues with the preserving rivers, streams and natural wetlands. There are a lot of natural wetlands that have gone extinct. Flora and fauna as native ecosystems, that is also has gone extinct. So, when we think about the ecological paradigm of the sustainability, we think about the natural system and think that what is that can be preserved while we are making the economic growth in our society. The next one is the social paradigm. So, when we think about some of the civilizations that were really advanced in the past but declined. So, an example is the Western Roman Empire, Empire on the Angkor Wat, and the Harappan Indus Valley civilization, which is very close to India. We know that these civilizations were very well flourished and were very well functioning societies. However, they have completely gone extinct and have collapsed. So, mostly if you read the literature, you would see that mostly the collapse has been reasoned by climate impact, environmental damage, resource mismanagement that weakened the empire, leading to successful invasions. But is that all? There has also been a recent decline of political nations such as Soviet Union or the splitting of the nation, and there are of course other factors such as the human factor that also leads to the decline of the civilizations. So, when we think about the three spheres of sustainability, environmental, economic and social, each of that has their own focus. So, the economic is more focused on the profit, economic growth and all the R&D that is related to it. The environmental is more related to the natural resources use, environmental management, pollution prevention, all of that, and the social is more about the quality of life. When we think about the intersection between these spheres such as environmental and economic, we talk about things like energy efficiency. When we think of energy efficiency, not only is it addressing the concerns in the environmental sphere of sustainability, but it also helps in the economic, because you can increase your profit by doing more with less energy. Similarly, when we are thinking at the intersection of the social and environmental, we have environmental justice, natural resource stewardship, and locally and globally, we are looking at how can we maintain the societies and communities that can function well with the environment. And then the last is the social and economic. So economic and social is the business ethics, fair trade, and workers' rights. So we have seen that how these different things are important for maintaining the sustainability of the overall systems. And when we are thinking about any sustainability challenge, we do think about these three different pillars. How does that challenge affect the economic sustainability? How does it affect the environmental? And how does it affect the social sustainability? With this understanding, let's do a quick 30 seconds thinking activity. So in this activity, I urge you to think about a polluted river, any river you can pick, Ganges or any other river, and think about which pillar of sustainability is actually affected by that polluted river. Solution. Hope you all have some points to match what I have on the screen. So obviously, when you think about river, you think about ecological system. So when we are thinking about how a polluted river affects the ecological sustainability, a polluted river disrupts the ecological life within aquatic systems. So that is where it affects the ecological sustainability of that whole region. That is called as a direct impact of the pollution or the polluted river. Next, it can also affect economy, because if you have a polluted river and you are disrupting the ecological life, you will have declining fisheries and fish production, on which lot of the fishermen livelihoods are relying. Also, there can be, if you are withdrawing water from that river and it's polluted, you will have a high cost of water treatment, and that cost actually adds to the cost of water, purified water that you are buying. There is also diseases that can spread because of the polluted water, and that causes the rise in the healthcare because it is affecting human health. Hence, these are called the indirect impact. So, indirectly, even though polluted river does not directly view how it is working in the economy, but you see various aspects of the economy can indirectly depend on these ecological systems, such as here the fisheries, but also how we rely on that ecological systems. On a freshwater river, we are relying on getting water, and if it is very polluted, we are getting high cost of treatment. And the last is of course, the social. If you have a polluted river, of course, you don't want to go and sit on the banks of that river. So there is lack of recreational activities. People disengage with their natural system, and hence there is lack of knowledge of river, and there is all this indirect impact. So of course, all of this is causing ecological, economy, and social challenges, and any sustainability or anything that we see, we can think of different pillars or different dimensions of sustainability that are affected by that particular challenge. Okay, so now we understand what sustainability means and what are the different pillars or different aspects of sustainability that we need to think about. So the next question is that how do we account for impact on environment considering interaction of all spheres? So when we think of accounting for impact on environment considering interaction of all spheres, the first equation that came was the IPAT equation. It's called the impact equation. So it was the earliest approach to explain the role of different factors in environmental degradation. It brought the attention to the fact that technology and society interact to result in environmental degradation, and hence if we want to really reduce the impact on the environment, we have to target all of this. Of course, it is kind of combining the pillars of sustainability into one equation, and you can see if you change different levers in the whole system, how much is the impact that is being affected. So, total environmental impact, the IPAT equation. The equation reads out as the impact is equal to population, affluence and technology. Population is what we call as the social dimension. So, as society grows, we have growth in population. The second one, which is the consumption per capita, is related to the affluence. So, social and economic well-being is captured by this parameter. So, you can think that as the affluence in the society grows, your consumption per capita is increasing, and hence there is the economic aspect of the society that is being captured by this parameter. The last one, which is the technology, here we have pollution per unit consumption. So, now based on what technology we are using, we know we are creating some pollution for any product that we are using. So, that is basically an ecological issue, and this is technology driven. So, of course, we have social, economic and the ecological aspect of our consumption patterns captured in this one equation. Of course, we can think of how we are affecting. So, our population is increasing, consumption per capita is increasing more rapidly in of course developing economies, but developed economies already have very high per capita consumption, and then pollution per unit consumption is basically decreasing. So, we are definitely making strides into improving in efficiency, cleaner energy source, and also there are of course more opportunities here for faster impact. So, we can see that how different aspects are affecting the impact. Let us see the differential form of IPAT. So, what this equation says, delta I by I, all you have to do is take the first order differential of that equation, and what it is saying is that percentage change in environmental impact is affected by population growth rate, affluence change in terms of GDP or per capita income, and improvement per change in the technology. So, our current population growth rate is about 1%, our current GDP growth rate is about 3%, which means that if we have to even just maintain the impact, not increase the impact on environment, we will need to make at least 4% decrease in the environmental impact. So, you see that there is this equation tells that how different pillars are playing into contributing into impact, and how much decrease or how much improvement in one aspect you need to make to reduce the overall impact on the system. So, here is an example of that. So, these charts are showing the energy intensity change from the International Energy Agency or IEA report, and so the figure 1.1, the blue bars are showing how we have the annual change in energy intensity for the world. So, by 2016 to 30, it is considered that we will reduce by minus 2.5%, and on the other chart you can see the ton of emission per thousand in terms of 2010 USD. You can see that there is of course in the OECD countries we have about minus 2.2% reduction or 2.2% reduction in the tons of emissions, while in the non-OECD countries we have even larger 3.7% reduction. However, we know that energy consumption and emissions are increasing globally, which means that we are definitely making strides in improving the energy technologies to reduce those emissions overall. However, we are seeing energy consumption increase and hence emissions increase. So, your delta I by I or the impact is actually increasing even though we are making huge strides in the technology part, which means that we need to of course play with the other levers so that we can reduce the overall impact of our energy systems. So, another IPAT example is, let us say how much is the gasoline used in cars. So, total gasoline will be number of cars into miles driven per car and into gasoline per mile. So, our number of cars is the population, miles driven per car is service provided per car, and gasoline per mile is dependent on what type of car you are driving. So, it combines the effect of society or the population, service provided per car which is the economic part, and then the technology which is the economy and ecology part or the emissions part. Similarly, if you have production of any commodity, say energy, so for that you can calculate the impact as units of energy produced multiplied by impact per unit of energy products. Okay. With this understanding, we'll just quickly do a simple exercise. So here I am giving you some example. So on the variables, you can see the vehicle efficiency in miles per gallon. In 2017, the miles per gallon was 36.6. In 2025, the miles per gallon was 54.5. Of course, there is a huge reduction or huge improvement in vehicle efficiency. That's about 32%, I think. And then we have fuel E10 emissions intensity, which is pound CO2 per gallon. That stays the same. So fuel emissions intensity has not changed, which is basically how much emissions has been actually emitted when that fuel is being burned. Then we have the population. Of course, the population growth. So it changed from 326,348 to 346,407. Usage of vehicle is vehicle miles traveled, and it is kept the same. So we can calculate the emissions per vehicle miles traveled. So 17.8 is how much is being actually I can write. So 17.8. So this is basically, if you think, is calculated as, so we have 17.8 divided by 36.76, right? So we are basically dividing the LbCO2 per gallon divided by the basically the miles per gallon. So you have miles per gallon, and hence you are getting the LbCO2 per miles. So emissions per vehicle miles travelled is 0.486 in 2017, and it is 17.8 divided by 54.5 equal to 0.326 LbCO2 per miles in 2025. So what I would ask you to take 30 seconds and calculate the total CO2 reduction from 2017 to 2025. Okay, let's see the answers. So total CO2 is 1.43 into 10 to the power 9 for 2017. So you multiply the LbCO2 per miles, which is your 0.486 multiplied by your total miles travelled, and then your total population, which is 326,348, which is the number of people. So in this case, we are getting 1.43 into 10 to the power 9 for your total number or total LbCO2, and in this case we are getting 1.02 into 10 to the power 9. So because if you look at the equation, is population times the A, which will be your emissions, and which is the number of miles travelled, and then we have LbCO2 per miles, which is basically the 0.4 or which is the technology part here. Okay, we multiply it by the population so that this vehicle miles traveled, oh sorry, this is vehicles mile travel per people. So this is how much is the vehicles mile travel per people in that year is. So total number of miles travel. So that's why we multiply with number of miles, sorry, number of people. All right. So let's look at this example. We have the variables which are vehicle efficiency, fuel emissions intensity, which is LbCO2 per gallon. Then we have population, which is number of people. You have the usage of vehicles, which is given by vehicle miles travelled per people. This number may seem a little high, but let's roll with it. And then we have emissions per VMT or per vehicles mile travel, which is LbCO2 per miles. So LbCO2 per miles is calculated as LbCO2 per gallon and divided by the miles per gallon. So, when you divide that, you get the LbCO2 per miles, and that is what we do. 17.8 divided by 36.6, that gives us 0.486 LbCO2 per miles, and then you have 17.8 by 54.5, that gives us 0.326. So, take 30 seconds and you can calculate the total CO2 reduction from 2017 to 2025. Alright, let us look at the solution now. So, the total CO2 emitted is 1.43 into 10 to the power 9 for 2017 and 1.02 into 10 to the power 9 for 2025. Let us see how we calculate it. So, we have the impact given by population times effluence times technology. So, our population is number of people. Effluence is how much is the usage of vehicle. So, you have 9,000, sorry, I will just write the variable. This is the miles travelled per people, and then technology is emissions per mile. So, we have LbCO2 per miles. So, when you multiply this LbCO2 per mile by the usage of vehicle, which is the miles per people and number of people driving, that gives you the total LbCO2. So, you can do the math, you can use this equation and match the number. So, you have 1.43 into 10 to the power 9 and 1.02 into 10 to the power 9. So, yes, there is a reduction in the total CO2 emissions due to the driving, but your total improvement is actually less than the technology improvement alone, as the total impact has contributions from other sources as well. So, for example, we have about 32% reduction or improvement in the efficiency, but our actual reduction in the actual reductions in the emissions is only about 28%. So, what IPAT shows is that just improving on one pillar of the sustainability equation does not lead to the intended impact as we would have seen. So, we need to of course consider all of those aspects. So, in summary, sustainable systems design will involve thinking about three pillars of sustainability: economic, environmental and social. IPAT equation provides a simple method to combine the three pillars and quantify impact of changes on overall impact. And the IPAT equation also shows that improving on one pillar of sustainability does not necessarily solve the overall challenge. So, there are other aspects that go beyond that we need to consider if we want to really design sustainable systems. In the next module, we will be going to understand how to expand the boundaries for decision making, and why do we need to expand the boundaries for decision making.